Topic of this video is graphs of polynomial functions. A polynomial function is a function whose terms are products of real numbers and variables. So it can be written in this form, and we arrange it starting from the highest degree to lowest, where n is a non-negative integer and a of n cannot equal 0. Because if a of n is equal to 0, then the polynomial is not a polynomial of degree n anymore. Coefficients, the number a0, a1, a2, a3, numbers in the front of the variables are called coefficients of the polynomial. The number a0 is called the constant term. The very last number that has no x next to it is called the constant term. And the number next to the very first term is called the leading coefficient. an is the leading coefficient or the leading term. Which of the following is a polynomial function? So first one, not a polynomial, because polynomials cannot have negative exponents or radical exponents for the variables. No radical exponents for the variables or no negative exponents for the variables, and all the coefficients have to be real numbers. So first one is not a polynomial. Second one, again, we have a radical exponent because it's the same thing as x to the power 1/2. That's going to be not a polynomial, because when we define polynomial, we did say that the n has to be a non-negative integer. It has to be an integer, cannot be a radical, and it has to be positive. It could be 0, which is for the constant term. Next, this example, number 3, yes, a polynomial, because all the conditions are satisfied. The next one is also an example of polynomial. So today we're going to learn how to graph these functions. Earlier we graphed second-degree polynomials, which are quadratic functions. The degree of a polynomial, degree is the highest exponent for the variable. That's called the degree of the polynomial. A constant function f of x equals c, where c is not equal to 0, is a polynomial of degree 0. For example, y equals 2. That's a polynomial of degree 0, because we can write it as 2 times x to the 0 power. A linear function, f of x equals mx plus b, has a degree 1. A quadratic function, f of x equals ax squared plus bx plus c, has a degree 2. A function with the degree 3 or more is just called a polynomial. They don't have a special name like linear and quadratic functions do for degree 1 and 2. Okay, so here we're going to identify the polynomial function, leading coefficient, and the degree. So here's a function given to me. And what is the leading coefficient? Leading coefficient is the very first number with the highest exponent of the variable, which is -2 is the leading coefficient in this case, and the degree will be 5. The highest exponent is the degree. Next case, degree is 3, and the highest exponent is 3, so that's the degree, and the number in the front of that term is 1. So leading coefficient is 1. What kind of curve? Polynomials have graphs that are smooth, continuous curves. That means you can draw them without picking your pencil from one point to another, and they go on forever in both the directions. A smooth curve cannot have a sharp corner. A continuous curve cannot have a hole or a break in the graph. No asymptotes like rational functions. So here's 2 examples of polynomial function graphs, a smooth continuous curve that you can graph without picking your pencil. Another example of a polynomial graph, smooth continuous curve, we can graph it without picking our pencil. Here are some examples which are graphs of not polynomials because of the hole here and the sharp corner here. Same thing in the next example, we have a sharp corner, so that's not an example of a polynomial function. Now we're going to discuss the end behavior of graph of a polynomial function. Graphs of polynomials, in the middle, they can be increasing or decreasing, but towards the end, they're going to follow a special behavior pattern depending on the degree and the leading coefficient. Okay, if we have an odd degree polynomial, it's easier to think about x to the third, but this is going to be true for every single odd degree polynomial: x to the fifth, x to the 11th, x to the 27th, x to the 71, every single odd degree polynomial. The end behavior is only decided by the leading term, leading coefficient, and degree. And behavior depends on leading coefficient and degree only. So if we have an odd degree polynomial and the leading coefficient is positive, then my graph and behavior is going to be, it's gonna go, when x becomes really, really large, y will become really, really large. When x becomes really, really small, y will become really, really small. So as x increases, y increases. As x decreases, y decreases. Okay. If the leading coefficient is negative, then the graph is gonna go like this. It's gonna, when x becomes really, really large, positive, y becomes really, really large, negative, or y becomes very, very small. When x becomes really, really small, y becomes very, very large. Okay, so that's the end behavior. So when we have an odd degree polynomial and leading term is positive, and behavior looks like this. When we have odd degree polynomial, leading term is negative, leading coefficient is negative, then graph looks like this. Next, when we have an even degree polynomial, how's the end behavior of the graph? Again, end behavior of a polynomial graph only depends on degree and the sign of the leading coefficient. If leading coefficient is positive or negative. Okay, that's all the end behavior depends on. So if we have an even degree polynomial, leading coefficient is positive, then my graph is gonna look like this. When x becomes really, really large, y also becomes really, really large. When x becomes very, very small, negative, y still becomes very, very large, positive. Okay. When we have leading coefficient negative for the even degree polynomials, my graph and behavior is going to look like this. In the middle, we can have twists and turns in the graphs, no sharp corners, but the end of the graph on both sides is going to look like this. No matter what is the degree of your polynomial, any even degree, it can be 2, 4, 6, 8, 10, 12, 14, any degree, even degree polynomial. When x becomes really, really large, negative. When x becomes really, really large, positive, y becomes really, really large, negative. When x becomes really, really large, negative, y becomes really, really large, negative. And behavior of polynomial function is how does the graph behave on far left and far right. Again, in the middle, you're going to have intervals where the graph increases or decreases, but eventually it's going to rise or fall without bounds as it moves to far left or far right. Now let's look at some examples of figuring out the end behavior. And keep in mind, end behavior only depends on the leading term and the highest degree in your polynomial. Always make sure you have arranged your polynomial from higher exponent to lower exponent so that you have it in the standard form. So decide the end behavior for this polynomial. It only depends on the leading term, which includes the degree and the coefficient of the leading term. So here degree is 4 and the coefficient of leading term is positive 1. Degree is 4. Coefficient of leading term is positive. Leading term coefficient is, I'm just going to call it leading coefficient is greater than 0. So that means and behavior of my graph is going to be something like this. Again, we're not graphing it yet. We're just thinking about the and behavior. Another example, let's practice more on the and behavior. Here, degree is 3 and the leading coefficient is positive, which is 1. Leading coefficient is 1, which is positive. So for even degree, for odd degree polynomials, like in this case, our end behavior is going to be something like that. And of course, there's going to be middle tosses and turns in the graph, but we're only thinking about the end behavior. And we can write it as x becomes very, very large positive. F of x also becomes very large positive. As x becomes very large negative, f of x also becomes very large negative. Because as x is decreasing, as I'm going to the far left, y's are also getting smaller and smaller. As x is increasing, y is also increasing. Using the leading coefficient test to determine the end behavior of this graph, now we have the degree as 3 and leading coefficient is negative. So if the leading coefficient is negative, that means I'm going to have my end behavior for the graph is going to be something like this. And of course, there's going to be tosses and turns in the middle. We don't know what that is going to be, but I'm just thinking about the end behavior right now. Okay, end behavior is going to be like when x becomes really, really large positive, y becomes really, really large negative. When x becomes really large negative, y becomes really large positive. Polynomial functions, real zeros, graphs, and factors x minus c. So for a polynomial function, if p is a polynomial function and c is a real root, then each of the following is equivalent. X minus c is a factor of p. X equals c is a real solution of p of x equals 0. X equals c is a real zero of p. C0 is an x-intercept for the graph. Here's an example. I took an easy example for a quadratic polynomial. Y equals x squared minus 5x plus 6. So if I have an equation, if I go ahead and factor x minus 3, x minus 2. So x minus 2 is a factor. That means x equals 2 is a 0. So if x minus 2 is a factor, x equals 2 is 0 for the polynomial, x equals 2 as an intercept. And if I were to solve 0 equals x squared minus 5x plus 6, then my two solutions would be x equals 2 and x equals 3. So all these are equivalent, that the x-intercepts, roots, solutions, zeros are all the same numbers. If x minus c is a factor, then again, if x minus c is a factor, then x equals c is a real solution of the equation, x equals c is a 0 of the polynomial, and x equals c will be the x-intercept of the graph as well. We can write it in the coordinate pair form as well. Zeros of polynomial function. If a polynomial is of degree n, it can have at the most n real zeros, including complex and rational zeros. So function of degree n has at most n real zeros. Zeros can be found by factoring the polynomial. The graph has a graph of degree n can have at most n minus 1 turns. So if a graph has a degree n, it can have at most n minus 1 tossing and turning points in the middle. Those turning points are called maximum and minimums for the graph. And they change the graph from increasing to decreasing or decreasing to increasing. Here's an example. So this graph has how many turning points? This graph has 3 turning points, and that means there's the degree of this graph will be at most 4. At least 4, sorry, because a graph of degree n has at most n minus 1 turning points. So a graph of degree 4 will have maximum 3 turning points. A graph of degree 5 can also have 3 turning points. A graph of degree 6 can also have 3 turning points. So a graph of degree n has at most n minus 1 turning point. So if I see 3 turning points, then the degree is at least 4. It could be more, but at least 4. Next, we see 1, 2, 3, 4 turning points. So degree is 5 or more, at least 5. And what tells me leading coefficient is going to be positive? Because my graph is an odd degree, it goes it follows the end behavior of an odd function, and it would be a positive leading coefficient. In the previous one, I would have a positive leading coefficient as well because the graph is going up in both directions. Shape of the graph near 0 of multiplicity m. So sometimes we have a root which is a repeated root. So for example, for a polynomial, x can be a repeated root, or x minus 2 can be a repeated root. So if we have a repeated root with the multiplicity which is odd, so if we have a repeated root with the multiplicity m equals 1, my graph is going to touch. If c is a repeated root of multiplicity 1, then the graph is going to touch and just cross at that point. But if we have an odd multiplicity, but it's not equal to 1, for example, if the multiplicity, if my polynomial is p of x equals c, not p of x equals c, it would be p of x equals x minus c times x minus r. I'm just going to make that up. So if I have the multiplicity which is odd, if the multiplicity of a 0 is odd, then and it's greater than 1, then my graph is going to do that slowing down thing around that point. It's not going to just cut through the axes, it's going to be slowing down at that point. For even multiplicity, your graph is not going to cross the axis at that point. It's going to touch and bounce back, touch and bounce back. Again, if the multiplicity is higher, for example, if it's 4, it's going to be a bit slower when touching and bouncing back. So you'll see a little flatter curve at that point if multiplicity is higher. Strategy for graphing polynomial functions: use the leading coefficient test to determine end behavior. Find x-intercept by letting y equal 0. Find y-intercept by letting x equal 0. Find roots, zeros of polynomials and x-intercepts. Check for multiplication of roots. If multiplicity is even, your graph will touch at that root and turn around. If multiplicity is odd, the graph is going to cross x-axis at that point. The graph will flatten out near x-intercept when the multiplicity is greater than 1. Maximum number of turning points a graph can have is n minus 1 if n is the degree. Locate additional test points and find corresponding values. Let's see some examples of graphing polynomial